Hi everyone, welcome to EI 2024. Today I'm very excited to have with us Professor Alison Okamura. She is a professor in mechanical engineering at Stanford University. I'm very excited about her talk that not only is going to enlighten us about robot-assisted surgery, but also will broaden our perspective on sensing and imaging to include haptics. So Alison, welcome.
All right, thank you very much for having me here today. I am a roboticist and mechanical engineer by training, so it's really exciting to talk to folks in imaging, both to hopefully inform you and excite you about what is going on in the fields of surgery, as well as haptics, which is human-machine interaction by touch. In addition, I'd love to get your feedback and ideas about how these technologies can become better integrated with imaging. All right, so since I'm talking to folks that are probably mostly interested in sight and vision, I would like to do a comparison between the sense of touch and what we can get from vision. These can parallel, they can overlap, but they can also be sort of dual in nature. So some of the things that I think about sight include the idea that you would have a centralized location where you can look at the world, at least for humans, our eyes. I also get a very broad view. I can stand up here and see all of you. Sight is relatively passive. All right, so the sense of touch in comparison is distributed. I have touch sensors all over my body, and interestingly, I'm very high resolution, a high density of mechanoreceptors in locations like the fingertips, whereas in other parts of the body, like my forearm, as well as the back, I have a lower density of mechanoreceptors. And this sense of touch is also relatively narrow, right? In order for me to have an interaction with the environment, if I reach out and touch this, then I'm feeling it through this one localized place. So these various properties of sight and touch can be brought together, of course. In some interactions that we have with the world around us, it's important to be able to utilize the dual nature of sight and touch in order to be able to have the best and fullest of interaction with the world, in order to reduce the energy that you have to output in a system, and basically optimize the type of interaction you have. And one of the places where I think this is really important is in surgery. Okay, so if any of you is squeamish here, let me just say that this is not real tissue. This is rubber and foam and nothing scary up there. What we're looking at is the close-up view of a teleoperated robot-assisted surgical system. The particular one that I'm going to focus on today is one that I have a copy of in my research lab. It's called the Da Vinci Surgical System. I didn't realize this was going to be sponsored by Intuitive Surgical, but it comes from that company. And the version that you're seeing actually in these videos is one of the very first versions that came on the market well over 20 years ago, about 25 years ago now, and is now used worldwide in procedures. But what I want to explain to you about what's happening in this video is that a human operator sits at a console, this is the surgeon, and they're manipulating these fancy joysticks which have 7 degrees of freedom. So they move in X, Y, Z, yaw, pitch, roll, and gripper. Okay, those are the 7 degrees of freedom. The patient-side robot also has those degrees of freedom, although they're not operated in quite the same way, but it can be moved at a much smaller scale. So although we have these side-by-side images, the scale of the top video is almost 1/10 of that in the bottom video. And it's amazing when you sit down at this robot and you teleoperate it and you're looking through the console and seeing images from the camera on the patient-side robot, you really feel like those are your hands, and hence the name of the company, Intuitive Surgical, right? You're really feeling like as you move, the patient-side robot moves with you. One of the things that I'm particularly interested in systems like this, especially coming from a mechanical engineering background, is understanding how the forces and touch interactions are important in order to make surgical procedures like the suturing happen here be most effective and safe. So However, what happens in the clinical robot is it's very difficult to actually provide force feedback. That would require force sensors on the patient-side robot, and then you need to push back on the hands of the surgeon. And there's a whole separate talk I could give about why those systems can go unstable and why it can be a little bit dangerous to close that control loop. But what I want to focus here is how do we get around the need to use force sensors on the patient-side robot? And one of the answers is vision. So the current clinical robots do not have very much haptic or touch feedback. Instead, the clinicians are mostly relying on looking at the images of what they see on the patient side and then making decisions and figuring out how to move based on that. And so humans are obviously using vision in place of the sense of touch, and we want to figure out how and when they can do that. So, for example, in vision, you can potentially get force information. You can see things like tissue blanching if you squeeze it. You can see the stretch of material, and you can also see the displacement of your own hands as you interact. And so in a kind of Bayesian framework for how people estimate some of the mechanical properties of objects around them, you can do things like say, well, I'm going to look at displacement, I'm going to look at force, there's going to be some probability distribution that will tell me what likely is going on. And then I can combine that with other types of information, not just what I see on the screen, but my own body's proprioception. So proprioception is our ability to know where our own body is in space and how it's moving without necessarily needing to know about the forces, but rather feeling in our joints and our muscles and our internal position sensors about what we're doing. So now this displacement and force information, after getting some sort of posterior estimate where we combine the information that we have, we can do these estimates where we combine force and displacement, and we use that to come up with estimates of mechanical properties of the environment. And so we know, because clinicians can actually use a robot like the Da Vinci surgical system without getting force feedback, that people are somehow able to do this. And so what we're wondering is, how can we do this in a more automated fashion? Now, the reason why we would want to do this is twofold, or at least from my perspective as a researcher. One is we'd really like to understand human performance. If we're going to optimize these engineered systems so that they can be designed better for people, we want to understand how people are combining information. In addition, just like with self-driving cars, there's a lot of interest in moving some types of surgical robotics towards autonomous systems. In that case, the robot itself has to know how you combine perception and action. And then there's this overlapping aspect, which is actually really important, which is evaluation. If we want to understand how well a surgeon-robot combo is performing in an actual surgery, and we want to know, for example, how well a surgeon has been trained and are they ready to go practice on patients, there has to be an evaluation stage as well. So I'm going to go through a few different projects that combine this idea of seeing and feeling in surgery and some of the things that we've discovered about what we can do with humans and also what we can do with robots. And the end of my talk, because I'm a mechanical engineer and I just can't help it, I'm going to talk about some new mechanisms and devices that are new to robot-assisted surgery and might also give you some ideas about how imaging might be involved. So I'm going to start with a project about understanding and developing force estimation in surgeons. So really, this is a kind of a neuroscience project, a psychology project, looking at how humans use this information. And this idea came from originally a concern from one of my surgeon colleagues, which was that as more and more clinicians move towards doing robot-assisted surgery without having trained with their own hands first, are surgeons going to lose this ability to estimate forces based on what they see? So if you have a novice surgeon and they've never experienced interacting with real tissues, how is it that they could possibly use vision in order to estimate forces if they have no prior experience of actually feeling forces? And even very experienced surgeons, like the one that's highlighted in this quote here, is that the surgeons often feel, with operating a robot like the Da Vinci, they think that they're feeling forces, even if they're not actually receiving that feedback. In fact, the DaVinci system has a passive spring in the gripper of most versions of the system, and clinicians will always tell me how I love that haptic feedback on the gripper. I'm like, oh, that's just a spring. But it's something that the user will imbue with these other properties because the whole experience of doing surgery with the system is so compelling. So there are many different types of surgery that have different levels of feedback. RAS is robot-assisted surgery. Laparoscopic surgery is minimally invasive surgery done with manual handheld tools. And open surgery is when you actually cut open a patient so that you can put your hands inside of them. And they all have different levels of interaction, difficulties with tool movement, changes with movement scaling, and the level of haptic or touch feedback that a surgeon can get. And so what we're wondering is how do these different experiences start to translate from open and laparoscopic surgery into doing robot-assisted surgery where you lose that haptic feedback unless it's directly programmed into the system. So we did an experiment first using our a research version of the DaVinci surgical robot that we have in our lab and doing a couple of different tasks. One of the tasks, which is what we focused on people learning, was simply pulling on artificial soft tissues and having people learn to associate forces with what they see in the image. And we even did very simple things like you can see the color slightly lightens when it's stretched, and that's to mimic the blanching of tissue, but that's an artificially changed visual so that it looks a little bit more like real tissue and changes in the way real tissue would. And then we also tested a novel task that we didn't train on, which is palpation. So often clinicians, when they're trying to learn if there's a hard lump in soft tissue, they'll move their fingers around and sometimes also use vision in order to try to figure out if there's a hard lump inside soft tissue. So when we do these types of procedures, we are first going through a training phase where we try to teach people, for example, to do manual manipulation. And in this manual manipulation, the user's directly pulling on the artificial tissue. And then we do teleoperation with haptic feedback. Because we have a research version of the robot in our lab, we can actually program it to give haptic or force feedback to the human operator, but that's not something that is very easy to do within a clinical system where you don't want to have to put expensive, delicate force sensors onto a clinical robot. And then we have teleoperation without haptics, which is mostly what it's like in the actual operating room. So we do these training conditions, and then we also evaluate teleoperation with haptics. So this video will hopefully play automatically so you can get an idea of what it looks like when we are having users go through this process. We're looking at how well people are able to estimate the forces that they're applying to the environment. We measure how much error they have in their force, how much time it takes them to complete a surgical movement. I highlight this particular metric here, the normalized absolute error time, just because that's a way of combining both the errors people make and how long it takes them. Because if you think about it, the goal of improving your skill is to get better at doing a task and also doing it faster. But there can be trade-offs, right? You don't want someone who learns how to do a task faster but makes more errors, or learns how to do a task more accurately, but then it takes longer. Ideally, you want to combine these error and time metrics, so this is going to be the primary metric we talk about. And then there are some other metrics that we can also use that have more to do with the details of manipulation. So briefly, one of the results from this work is that if we have users performing this task, we found that users can't actually develop really an internal model of stiffness without having had an experience of touching real objects first. So they come up with a kind of proprioception force heuristic, like based on how they move, they have sort of an assumption of how much force is being applied, and they're not truly having an understanding of what the mechanical properties of the environment is that they're working with. And we found that among these different training conditions, if you teleoperate with or without haptic feedback versus when you train with the manual system where you're directly touching the environment, the manual training is best. So that actually highlights that the surgeon we worked with, they're concerned that if someone goes directly into robot-assisted surgery without ever having manually interacted with real-world tissues, that might actually create some problems. Now, lest you worry about your next Da Vinci surgery, that doesn't yet happen in clinical training. Right now, everyone does still train first with manual procedures. But there will probably become a day where we no longer train directly on physical tissues, but rather work always with a remote robot. And so some other training paradigm is going to have to be brought into play in order to teach people how to do this force estimation from vision. So the palpation task, the goal there was to take training in a different task and then see if people can adapt or generalize to doing a different task. So they trained under this pulling on tissue task, and now they're trying to palpate in order to come up with some estimate of the tissue properties. And in this case, we found that the manual condition, again, was significantly better at helping people learn how to perform the task. So even when we move to a new task, this same kind of learning can persist, but you need to have had some manual intervention first. So the big picture takeaways from what we got from this human-related experiment was that you can't take for granted that there is a visual haptic learning process that helps people connect what they see and what they feel. It doesn't always generalize from one task to another, but it will help if it's a manual task. I didn't get into this in detail, but as I mentioned on the very first video, there's a motion scaling between how the surgeon moves their hands and how the patient-side robot moves. And this can affect the visual haptic learning, and so you might need to learn at different scales. Some versions of the Da Vinci surgical robots, you can sort of switch a dial to change that scaling factor, and so if you change that scaling factor, people will have to learn and adapt to that. And in general, we would ideally not have to do these types of experiments at all, right? We would take what we know about human motor control and human sensory motor learning, and we would apply it to surgery. But one of our big lessons as we also talk to people in the neuroscience community is that so many of the experiments that are done to define how people do motor learning tasks is done in these very rarefied environments where people are just making simple reaching movements. And even the movements I'm showing here are quite simple. When you get to more skilled tasks like suturing or anything where you have to make multiple motions, especially with multiple hands, there's very little known about sensory motor learning in the neuroscience literature to inform us. And so there's hopefully going to be a better connection between these applications and what we know about human performance in the future. So our big question here is what happens in a future where there's less prior experience? This is something that we want to be sure we get surgeons trained correctly, and maybe that can be done with a surgical robot, or maybe it's still done with manual tasks. And then autonomous systems can also take advantage of this, right? If people can learn based on prior experience, can we do learning for autonomous systems? And I'm going to skip ahead to the next section, which is talking about how we do force estimation through machine perception. So I should say that there are a few groups around the world who are trying to do this task, which is to basically look at tissue deformations and use that to estimate the applied force. That can do a couple of things for you. One is it can remove the need to actually put a force sensor into a system that has a human in the loop, and then you could also go towards more autonomous procedures. So there are model-based methods, there are learning-based methods, and there are various methods use different inputs. But one thing that's key is that we don't necessarily only use vision in order to make these estimates, because if you also have the kinematics and the proprioception that a human has access to, and we have that information from the robot, we might as well take that and put it in the pot and stir it in as well when we're trying to do this estimation task. And here are a few examples of prior works that have tried to do this type of task. Our approach has been to use a convolutional neural network where we've been learning haptics from both vision as well as the state of the robot. Okay, so the state of the robot includes the kinematics of the robot as well as some, I would say, not super accurate torque estimation. It's not really a direct force sensing, but we know something about the motor effort that the robot makes as it moves its instruments around. Like we know how much current is being drawn and being applied to the motors, and that can be thought of as a rough torque estimate. So we have these different ways of estimating. Here, for example, vision plus state together. We take RGB images from the cameras, the kinematics and torque, combine these in various ways, and we come up with an estimate of Cartesian force. And we're grounding this against an actual force sensor that we put underneath our artificial tissue, which is, of course, not something you can do when you have a real patient. There's no way to put a force sensor in there. So this is just for training purposes. And then we have a simpler version where we're only using the robot's state and we are not using vision. And this gets to asking, how accurate is it in terms of just estimating forces from the robot itself? And then we have vision only, where we're throwing out the information that we get from the fact that we know we are moving a robot to interact with the tissue. So this is the setup for this type of experiment. We have the patient-side robot. Now, when I showed you the very first video, we just zoomed in on the tips of the instruments. But of course, the tips of the instruments are attached to a larger robot arm, which is shown here. Here's an example where the artificial tissue is laying on top of a force sensor. It's made of silicone rubber. In this case, we're just using a pair of cameras, but you can also use a real-world laparoscope or endoscopic tool. And we've also tested different tools, and we've looked at generalization across tools. So when we do this sort of estimation, here are the different conditions that we're comparing against. So the ground truth, the thick black line, is the actual force measured from the force sensor that's sitting underneath the tissue. The vision alone is the V, state alone is the red, and the vision and state together are here. The RNN and physics-based are actually comparing against some prior work. And these are hopefully aligned, this video of actually manipulating the tissue and what's going on in terms of the measurement and the different estimation techniques. So this is just really seeing how it runs, but let's look at the kind of outcomes when we summarize the root mean square error for these different procedures. So here we have, let's start with all, which means we're using all of the different configurations, different heights of the tissue, different orientations of the instrument, trying to be as general as possible. The various techniques, they don't do too bad. So this is error in newtons, so how much force is being applied. And it's all less than 1 Newton of error, well less in this all case. And you actually see that they're not too distinguishable, but vision plus state, the combined information, is better overall. Now, if you translate to having an unseen tool, like you trained it with a system with a particular instrument and then you switch to a different instrument that might grasp the tissue differently, then you can see the error is higher and the results are slightly different. And we also wanted to see what happens when you try to generalize to an unseen material. So let's switch from one silicone rubber to a different type of material, and that's supposed to mimic what happens if you switch from one type of tissue or surgical procedure to another. In this case, you see the vision error in particular can go way up, at least in this Z degree of freedom, and the state the state and vision plus state together are not so bad. Interestingly, in these other degrees of freedom, these are X and Y of the XYZ of the robot, actually state alone did better. And what you see over here is based on the learning algorithm, we wanted to look at what areas of the tissue were being, or of the image were being most focused on by the algorithm. And so these are just some examples of showing what is being looked at. And interestingly, it seems that what's going around the instrument tip itself is somewhat confusing and changeable. And so it seems to mostly look at how the tissue is moving in the area around where the instrument is rather than at the instrument location itself. So state plus vision, although not consistently, mostly results in better performance. we do think that we can get better performance as we invoke better algorithms, and also we need to make this happen in real time. We do think there's definitely the potential for overfitting in these methods, and so as we're able to collect more data and do this in an automated fashion, the hope is that we can get even better results. But the main takeaway is that, at least for the data I'm showing over here, the errors are not so large, and they might even be acceptable for surgical procedures. So I mentioned briefly that we wanted to do this more in real time, and we have done this. I think we still need to perfect it. But the goal of doing this type of estimation in real time is so that you can either do autonomy or you can use the output force to give direct haptic or touch feedback to the human operator. So here's some examples with some of the different feedbacks. So here is using the force sensor itself. So that one, which will come back around on the video, was the ideal case if you're directly measuring the force and feeding it back to the user. And then we had real-time estimates happening from vision state and vision plus state together. And you can see that we can get reasonable feedback. So this is both the real force sensor as well as the estimated force sensor, and all of this now can be done in real time. The hope is to continue improving this accuracy so that it can be done in real robot-assisted surgeries. One thing you'll note in some of these plots, you'll see have some high frequency vibrations in them, which is not good. And that is the edge of instability happening because of some of the time delays that occur when you're trying to do these real-time estimates. So for us, real time would ideally be on a millisecond scale, because when you're providing force feedback to push directly back on the hands of the clinician, you're closing a dynamic loop, and depending on how the user moves, that changes the instrument, and you have to make that loop happen very fast in order for real-time feedback to remain stable. So some of those vibrations that you were seeing in some of those cases are because our algorithms, the real-time ones, are not yet running fast enough. All right, so one other thing that we need to do if we want to move this into real-world surgeries is we need to have better force sensors. I showed that we had a force sensor underneath our artificial tissue, and that was a nice 6 degree of freedom expensive force sensor. And even in an artificial laboratory environment, that is not enough. Because if we want to do two-handed bimanual procedures, and you want to have one instrument pulling on tissue with respect to a different instrument, all you would get from a force sensor that's underlying the artificial tissue is the net force applied from those two instruments. So if you want to start understanding bimanual techniques, each instrument actually has to have its own full 6 degree of freedom force torque sensor. And this might not sound like a difficult thing to do, but it's actually pretty hard to make high-quality force sensors at this scale of force that can go onto surgical instruments. And not just one per instrument, you actually need two per instrument, because you need one on each side of the gripper so that the jaws of the gripper, you can see how they're interacting with each other. So if anyone is interested, we have now an open source force sensor that can be attached onto robots like the Da Vinci surgical system or any other type of robot. It could be scaled up. I don't think we can make it any smaller, but it can be scaled up. And we've been able to now use this to start to tackle these problems for bimanual multi-degree of freedom manipulations. And if anybody wants the QR code later, feel free to come see me afterwards. So I want to end this section of the talk with just a little bit of a description of where we think surgical instruments themselves are going, and this might present some interesting challenges for folks who are in the imaging field. So there are lots of different ways to make snake-like instruments that can get deep in the body. You can see the types of instruments we showed before that are attached to the Da Vinci surgical system are relatively stiff and straight. Intuitive Surgical, as well as many other companies, have started to make some kind of curved robots. But it is challenging to get these robots to go very deep in the body because of the friction of the instrument with respect to whatever vasculature vessel you're trying to travel through. So to spark your imagination, I'm going to show this example of a soft growing robot. Imagine you have a material that's like the consistency of a Ziploc bag, and you put it into a tube. If you stuff that tube inside of itself, and then you pressurize it with air or saline solution or any fluid, then it will emit out of the tip and grow. And so we've been doing this not only outdoors, we can grow these things the length of a football field. We're trying to start a company to use it for pipe inspection. But some of my former students are now using this in medical procedures as well. So here's an example of an intubation device where this robot, I'll call it a robot in quotes, it's kind of more like a plastic bag filled with air than a robot, but you can see that it extends, and you can imagine there's no friction when you try to push it inside the patient because the new material just comes out of the tip. So this has been very successful in intubation, and one of my former postdocs is starting a company around that. And then we've also been making really small ones. A former student of mine at UC San Diego is now making ones which, let's see if I can get this video to replay. There we go. So this is only about 1.5 millimeters wide, this same kind of soft-growing robot. And it can be pre-shaped. If you have a preoperative image of the patient and you know the path that you need to go through, you can pre-shape it so that it exactly grows into that path. And then you can also use various steering mechanisms in order to get it to go into different locations. So these are kind of a new class of type of robots that we think will be great for various types of interventions. They are not yet, I would say, surgical systems or true interventional systems yet, but they'll need to be integrated with imaging and other types of sensing in order to make them successful. So you all might have some ideas there. So the last part that I want to talk about is more about the haptic feedback side. How does the user feel something from a teleoperated robot, whether it's a virtual environment or in a surgical scenario? So we've been working over the years, let's say we started with desktop haptic devices, and we've been moving towards a technique called skin deformation feedback, where you sort of subtract off the net forces applied to the user, and what you're left with is local skin deformation. And this sort of information can be displayed in a wearable form factor, and I'll tell you a little bit about the path to get there. So what's shown in this image is a classic force feedback haptic device. It sits on your desktop. Probably costs $10,000 to $20,000 because it uses super expensive Swiss motors. And the idea is that it has multiple degrees of freedom, and anywhere in the workspace it can apply a desired amount of force to the human hand. So it looks very similar to a robot, but it's purposely designed to be back drivable so the user can move it around, and that can precisely apply a certain amount of force to the user at a particular place in the workspace. Now, those devices mainly focus on force feedback. We're going to switch to thinking about stimulating the skin rather than pushing on the whole hand or arm. So these videos here are showing the effect, how effective or important cutaneous or skin-based sensing is for people. So on the left here, we have a video of a woman striking a match. You can see that these are very old videos from the late 70s, early 80s, just based on the hair and outfit. But the idea was that they discovered how important this cutaneous sensing was by having people perform a normal task, like lighting a match, and then just providing a local anesthetic to the skin of the fingertips. So what you're seeing on the right here is this subject trying to perform the exact same task. She has all of her dexterity, she has all of her vision, she can still feel any large-scale forces, and the only thing that she is missing is the local contact force at the fingertip. And she does eventually get a power grasp on that match and is able to light it, but it's a very difficult task. And this just really highlights this kind of underappreciated nature of the cutaneous sensing in our skin. And right now, that's not really used in many virtual environments, and in particular in like the robot-assisted surgery examples I was giving. Those all use this net force feedback that pushes back on the whole hands and arms of the clinician. So what can we do with cutaneous sensing? Well, there's a lot that's going on in the skin. We have these various mechanoreceptors or sensors that are embedded in the skin, There are different types that have different density, different spatial distributions, different receptive fields. They can respond to different frequency. So one example is we have something called the Pacinian corpuscles that loves high frequency information. So when your cell phone vibrates because someone is calling, or even higher frequencies, for example, the frequency I just feel from tapping over a surface like this, the Pacinian corpuscles are really happy. But some of them also do work with relatively low frequency information. So if, for example, if due to friction I'm sliding across a surface, those minute changes can also be noticed by other types of mechanoreceptors. And as I mentioned at the very beginning of my talk, haptics on our bodies varies depending on where you're looking. So we have a very high density in the glabrous or non-hairy skin of the fingertips, but in other places where we would also like to stimulate the body to have wearable devices like the arms. I don't know about you, but my Apple Watch, I don't feel the vibrations that well from it, and it's because it's in an area of the skin that doesn't have nearly as many mechanoreceptors. So we also want to understand if we're going to provide these feedback devices, where do we put them in the body and how effective will they be? So I'm going to start with this skin deformation example. All right, this will play. So this is one of the first skin deformation haptic feedback devices we built, and it's basically like a little delta-shaped robot that you put on your fingertip. And it stimulates the skin in 3 degrees of freedom, so normal force as well as shear. And then, let's see if this next video plays, we can have people manipulate objects in virtual environments and feel the skin deformation feedback. And the interesting thing about it is that this cutaneous feedback alone, just stimulating the skin, people can do a really good job of manipulating virtual objects with this. So you can get away from these really heavy desktop manipulandum type haptic devices and now have wearable devices such that if you pick up a virtual object, you can feel it tugging on your fingertips. Now, interestingly, when my student Sam here is grasping these virtual blocks, there's nothing preventing his fingers from passing right through each other, right? There's no force feedback that's keeping his fingers apart, but just the cutaneous stimulation alone is giving him the right feel so that he can perform this manipulation task. So we've been trying to improve on these devices, sometimes trying but not necessarily succeeding. We thought, well, that last device I showed you was really hard to put together. My student had to assemble things under a microscope. And there was this hot area of soft robotics called origami robots. And we thought, well, maybe we can make an origami robot. That'll be easy, right? You just put it down and it'll all fold up into a nice device. Turns out we couldn't really make it any smaller and that much lighter when we used traditional techniques. So I would say origami was an interesting experiment, but kind of a bust. What has been successful, though, is really utilizing new 3D printing techniques, including embedded 3D printing, where you can actually print into a soft gel bath, which means you don't need support material. Some people call it zero gravity 3D printing because the gel will hold the thing that you print into place. And when you do that, you can create more complex shapes. You can kind of print in an inside-out fashion rather than just layer by layer. You can have things that point, surfaces that point in different directions as you lay down material. And this is an example of a pneumatic-based wearable, now 4 degree of freedom haptic device, because not only does it do normal force and shear, it also does a twist degree of freedom. And it turns out twist is actually pretty important when you're grasping objects, because objects will often slip from your grasp because they rotate before they fall. So this is one example of a fingertip skin deformation device. Now, one thing I will say, since I am partially in the field of soft robotics, is the dirty secret of soft robotics is they're almost always driven by pneumatics. And you can see these lines here that are going off to the giant building compressor, which is not actually a wearable device, right? However, I will say that after a few years of me really worrying that maybe we were backing ourselves into a corner by using pneumatics, we do now have wearable pneumatic supply systems that can simply be mounted on the arm or mounted next to a robot or a virtual environment if that's what you're using. So these 3D printed skin deformation devices are lightweight, they're cheap, they're really easy to make when you use new embedded 3D printing techniques. So what else can we do? Let's see, I'm going to skip ahead a tiny bit. So those were all for the fingertips. And I mentioned that when I wear my Apple Watch and it's giving me vibration feedback to tell me something about where I should navigate, it is hard for me to notice. The vibrations are also, in some cases, supposed to kind of give me an indication of which direction I'm supposed to go, and I'm not really able to tell that at all. By the way, your sense of touch diminishes greatly with age. So my daughter can actually tell what direction the vibrations are telling her to go, but I cannot tell that. So this idea that we would like to get haptic devices off the fingertips so that we can put them in other parts of the body so they can be more easily wearable is a challenge because we don't have such great cutaneous mechanoreception in these other parts of the body. So we want to do this haptic relocation. Oh, and I should say one other reason is not just mobility and wearability, but as we do more augmented reality, number one, when you have all sorts of weird devices on your fingertips, it becomes hard to track the hands. And number two, if you're doing augmented reality and you want to touch real objects and then touch virtual objects, you can't touch the real objects if you already have a thing on your finger. So our goal is to say, can we trick users into thinking that they're getting touch feedback from virtual objects that are, I guess, embedded in real environments if it's augmented reality, or they can just be virtual objects, by displaying the haptic feedback to other locations of the body. And so our preliminary results are that you can do this. There are a lot of different mappings that you can have, like, oh, you can map this finger to a feedback here and this finger to a feedback here. You can swap, you can have all sorts of different mappings. And it turned out that people could adapt pretty well to all of the mappings when they performed a virtual pick and place task like the one that was showing on that video. But people do actually, if you just ask them what they like the best, they prefer the mapping that you would expect where things are spatially aligned. But it's always really impressive how much people can learn in terms of if you give them a new mapping, they can adapt to it, but people prefer the mapping that you would expect. So anyways, it turns out that by putting these haptic devices on the forearm or the wrist, at least for very simple grasping tasks and applying normal force alone, you can do this haptic relocation. And not only can people perform tasks, but they can even do things like estimate the mechanical properties of the materials, which is kind of neat when you think about it, right? You can grasp a virtual object like this. Your fingers are not touching anything. You get the feedback here, and people can sort of integrate the proprioception from their fingers to the feedback they get here in order to come up with a kind of model of what the mechanical properties of those virtual objects are. So we have been trying to take some of our 3D printing ideas. We're calling them haptic voxels, sort of like pixels, but they're 3D, and going from the ones that we've designed for the fingertips to ones that maybe can be rings that go on later on your fingers, or ones that can be applied to your wrist. And there are ways to make these without pneumatics, but we are feeling very confident that pneumatics is the way to go for us for now because we're now being able to make these portable pneumatic supplies. All right, so with that, I think I finished in time. So hopefully you've been interested in this journey from thinking about robot-assisted surgery in particular and how force and vision are combined in procedures like this, going towards the design of new devices, both for doing interventions as well as giving haptic feedback to human operators. And I'd also like to thank the sponsors of this work and our collaborators and all my students who actually did the work. Thank you very much.